This is lesson 31 of the no-nonsense A-level physics lessons. And this lesson is all about vectors and scalars. So just a reminder, we've been working through lessons for quite some time now. This is lesson 31, and all the lessons consist of is me and a whiteboard, just me talking and writing on the whiteboard. And that does a few things. It forces me to slow down, giving you time to absorb the information, but also giving you time to record the notes yourselves. And by limiting each lesson to a single A4 page of notes, it means that what I'm covering is realistic within about half an hour per lesson. So vectors and scalars at GCSE level. You learn about vectors as an irritating bolt-on extra. There's not really much point having it at GCSE level, or at least that's how it feels. You'll learn that velocity is just speed in a particular direction. And you'll learn that displacement is just distance in a particular direction. And you'll be scratching your head and wondering why you bother with the direction at all. Your teacher might say to you, what is the velocity? And you'll give an answer, and then they'll waggle a finger at you and say, but what's the direction? Because it's a vector. And it will just feel irritating. But actually in A-level physics, the vector nature of quantities, of vector quantities, becomes really, really important. So yes, we know some of the basics from GCSE, the idea that vectors have a direction as well as a magnitude, whereas scalars don't have a direction. Scalars just have a magnitude. Might as well get this in the notes so that we've got it there. Vectors have magnitude and this is the important thing, and direction, but scalars have magnitude and no direction. Okay, so a quantity could be a scalar quantity. What does that mean? Well, it means that the quantity has 3 bits of information. It'll have the numerical value that we assign to that quantity, which gives you some indication of the magnitude. It will have a unit, which also gives us some indication of magnitude. A meter is very different from a mile. But also it will have the dimensionality of the quantity in that unit. In mathematics, they tend to include the units separately, auxiliary to the variable letter. So in mathematics, they might write something like x meters. We wouldn't tend to write that in physics. The x would be a quantity containing the numerical part, but also containing the unit, and the unit contains the dimensionality of the quantity as well. Vectors have 4 bits of information. They have the numerical component, which gives you an indication of the magnitude. They have the unit, which gives you an indication of the magnitude. They give you the dimensionality, which is included within the unit, but they also include the direction. So vectors and scalars in equations, we would tend to just write them as letters. But there's a difference. So we would represent a scalar as just a letter, but a vector, we could represent it as a bold letter in printed text. So if you ever see printed text where the variables are written in bold, that means it's a vector. We could also represent vectors with arrows over the top. This tends to be in handwritten notes, or with a underline is another popular one, or even a wiggly line over the top will indicate that these are vectors. And there's a special kind of vector called a unit vector that has a circumflex, a little arrow over the top, but we're not talking about that today. So these are just how we would represent vectors to make it clear that they're vectors when working algebraically. So for example, in the equation F equals ma, very famous equation that you will know from GCSE level, The m is a scalar, but the f and the a are vectors, and we can indicate that with arrows over the top, or in printed text we might use bold letters, or we can underline them, or we could do little wiggly lines over the top of them to indicate that they are vectors. My preferred one in recent years has been to draw an arrow over the top. I'm not sure whether that's academically the preferred method, but that's something that I've rather liked to have adopted. But when I was at university, I used to just underline vectors. That's how I would indicate it. Okay, so we've had a little bit of a waffle on about vectors, and we've got a reminder of some quantities that are vectors. We might as well bung this in a quick table. Maybe no set of physics notes would be complete without a NAF table like this. So let's put scalar and vector, and a quick table with some examples of these. So scalar quantity, we might have distance, and a vector quantity we might have displacement. And if we are asked to define displacement, we could say it's just a distance in a particular direction, but that's good enough. We'll have scalar, we'll have speed, and as a vector we'll have velocity. If we're asked to define velocity, it's a speed in a particular direction, and that's good enough. We've also got loads of other vectors that we should include, like force and acceleration, but interestingly not deceleration. Deceleration is the rate of reduction of speed, and so it should be in the scalar category. I'm not going to put duration, I'm not going to put time on these lists because that gets a little bit complicated. Time is the name of as a dimension in the sort of four-dimensional sense, where we have up, down, left, right, forward, backwards, and then we've got time processing what we might colloquially say forwards and backwards. I don't know how else you'd describe it. So time would be some sort of coordinate. But we also have duration, and often the word time just means duration, which is an interval along that time axis, in the same way as a displacement is an interval along a spatial axis. So when we say time, we might mean a vector, but is it a vector when there's only one temporal axis that we can work along? Well, I suppose technically, yes, it's a one-dimensional vector. So in that sense, time would be a vector, but it could also just be a dimension. So I won't put it on this list because there's no point. We've got things like magnetic flux density, which are vectors, but we've got magnetic flux, which is a scalar. We've got area vectors as well. Current, interestingly, is a scalar, even though sometimes we refer to the direction of current, making it a sort of pseudo vector. But no, current is a scalar. Potential difference is a scalar. Energy is a scalar. That's a common one. Let's get that one on the list, actually, because we don't get far in physics without thinking about energy. And I'll leave the list at that. You've got the basics there. And let's just make it into a nice, neat table, which will be helpful for our revision or something. There are lots more quantities as I've listed them verbally, but I'm not going to write them down because I don't think there's much value to having a big long list like that. We'll cover those quantities as and when they come up in the normal course of these lessons. So why are vectors so important in A-level compared to GCSE level? Well, because all of a sudden the vector nature can't just be reduced to a simple one-dimensional, or in difficult GCSE questions, two-dimensional situations. We now need to be able to understand the nature of the physics itself. We'll take force as the classic example. Forces acting in different directions, we still have to add the effects of those forces together. In GCSE physics, not GCSE double science, but GCSE physics, you may well have been doing graphical methods of adding force vectors together. And that's fine, that's very useful, but we need to be able to do it algebraically as well. The expression I've heard, a bit of a mnemonic device that I've heard used to talk about how to add vectors. So I'm going to put addition of vectors and this is a GCSE method. I'm going to put in brackets the graphical method, which you should still know for A level. The addition of vectors. The mnemonic I've heard, I'm not massively keen on it. The main reason I'm not keen on it is because when I've heard it used, the individuals who have used it have very often ended up adding vectors wrong anyway, despite being able to recite this mnemonic. I'm not a fan of mnemonics, actually. But I'll add it here anyway. So, mnemonic, I think that's spelt wrong. Right, sorry. The mnemonic device is that you add them tail to tip or toe to tip, something like that, or tip to toe. I'll put toe to tip. Maybe that'll help you, maybe it won't. I don't think it's necessarily helpful. So let us suppose I've got some vectors. Let's draw some vectors. I'm going to draw a vector, which I'm going to label A. Here it is. That's a little bit longer than that. Let's have that as vector A, just like that. And I'll label it in a second. And then we're going to have another vector. Let's make it blue. And we're going to do it like this. And I'm going to label this vector B. So we've got vector A, vector B. Vector A I've drawn in red. And I'm representing these vectors in a graphical diagram as arrows. And why am I representing the vectors as arrows? Because arrows have a direction, just like vectors do, but they also have a magnitude, the length of the arrow. Now, what I'm actually doing here is representing a vector as a displacement vector. So these arrows could be displacements, and that's a very easy way to visualize the addition of vectors is by visualizing the addition of displacements. However, that's not the only type of vector we could represent graphically like this as a displacement vector. These A and B could actually be velocities. So we could have a body which has a component of velocity in the direction A of magnitude represented by that arrow, and a component of velocity in the direction B. All these could be forces. So we could be pulling an object in the direction that A is indicating with a force which is scaled with the length of arrow A, and also pulling the object in the direction that B indicates with a force which is scaled with the length of arrow B. Usually when you learn about addition of vectors graphically, you start with displacement, hop straight onto force. But at A level, we might have to add magnetic flux densities in this way, or momentum. Momentum's a vector, I forgot that one. Might be adding momenta in this way. So we have to be comfortable with representing any dimensional vector as a displacement vector in a diagram. So what I'm going to do is I'm going to add A and B together. I'm going to start by copying A, and I'm going to put that here. And then I'm going to copy B, and I'm going to pop that here, just like that. And actually, I'm going to move this a little bit because I want a little bit more room. Let's put this down here, and let's move this over here to about there-ish. And let's put some symbols in between. So what we are doing is we are going to add vector A to vector B graphically. We choose our scale, and we do it using a scale diagram. So using scale diagram, this is GCSE level diagram. We have to choose our scale, choose scale, oops, and then the magnitude of vector is, well, the vectors are represented as displacements. Let's put it that way. So vectors represented as displacements. And because I'm limited to two-dimensional paper, I'm representing them as two-dimensional vectors in a plane. So I'm adding A to B. What am I doing? Well, I'm redrawing B on the end of A, as you can clearly see from this diagram. Alternatively, I could redraw A on the end of B. So if I start in the same place, just put B, oops, no, I should have duplicated that, shouldn't I? Let's undo the movement of B, and let's duplicate B like that. I could, oops, and now I'm messing up the size of B, and I don't want to paste it there. Oh, it's all going wrong. Right, duplicate that. I want to start in the same place. So for some reason, I've started in the lower part here. Let me indicate where I'm starting. And because I'm adding the red and the blue one, I might as well do that with the purple one. So I'm going to start here in this lower corner there. And I can either draw A from that point and then add the toe of B onto the tip of A, just like that. Or I could start by drawing B, and then I'm going to add the toe of A onto the tip of B. So let's just copy A. And, oh, I did it again. I will get better at this. I make no promises. Right, duplicate, and then very carefully grab it. There we go. We'll draw it like that. Okay, so you can see I've got two different paths, if you like, two different components of my displacement. I've got component A and component B, which when I add them together, I end up on the top left, I guess. Or I could have done the component of B plus the component of A, and I end up in the same place. And very often what I see is students will mess this up, and they will draw an arrow going across here somewhere, and that doesn't make any sense, none at all. We started at the lower right, we're ending in the upper left, so let's just put end up here, E, M, D. And so our vector, represented with arrows, is a resultant vector is doing that. I'm going to put the arrow head partway along the arrows so it doesn't get it all messed up in the diagram. You can do that. The arrowhead can be drawn anywhere. So A plus B is that purple one that starts at the beginning of A and ends at the end of B, or starts at the beginning of B and ends at the end of A. Now, to me, that's easy. To me, that's obvious. But this could be a challenge. Some students do find the addition of vectors graphically challenging. And if that's you, the best thing you can do is to practice. Practice, practice, practice again and again and again until you don't get it wrong. I am actually just going to move this to the right slightly to give myself a little bit more room. There we go. So that's the graphical addition of vectors. But it turns out there's another way. Rather than just using a scale diagram and adding the components A and B like that, and that's what they are called, so perhaps we should label these components. Let's just write it here. A and B are components. And then we can say that the purple one, which we label it C. C is the resultant. So let's label it C in purple. And we can say that C is what we call the resultant, which just means we've added the two components together. Now these are vectors, so I should draw little arrows over them. There we go. A and B are components, C is the resultant. We've added A to B to get C. And notice that A and B don't have to be perpendicular. Now, if A and B are perpendicular, we can use some very simple trigonometry. If A and B are perpendicular, it's very straightforward. So let's say algebraically adding two perpendicular vectors. Algebraically, I think that's how you spell it. Could be wrong. Adding two perpendicular vectors. And we're going to use trigonometry. Now I should go back a stage actually, because in the graphical addition of vectors, we measured the length of C and used our scale to calculate what the resultant vector's magnitude was. But what about the direction? And in the graphical method, we just lift out a protractor and measure that direction. Whereas when we're algebraically adding two vectors, we've got to be a little bit more careful. So let's say we're adding two vectors. Let's use the same notation, A and B. We're going to add vectors A and B, and they happen to be perpendicular. So we have, let's have this one here, and let's say that this one here is vector A. Let's then get vector B, which is going to be here. Let's have it a tiny bit longer because I want to, no reason. Just like this. This is vector B, so I'm labeling it. And this is vector A, so I'm labeling it. And perhaps we could say that A is equal to, let's say, 3 units. Now, what is the unit? It doesn't matter. These could be displacement vectors, in which case it might be 3 meters or 3 centimeters or 3 inches or whatever. They could be forces, and it would be 3 newtons. We're still representing it graphically at the moment, so it doesn't really matter. And B is going to be, let's say, 4 meters, just for what I think are fairly obvious reasons. I've just chosen those numbers because you probably won't need a calculator to do the next stage. And those of you with a keen eye for mathematics will have already spotted why that is. Now, a very common mistake that I see students making is they will now think, well, I need to add those two vectors, and they'll draw a line like this. And that's obviously incorrect. Because if we were using the graphical method, we would clearly see that we would be redrawing B on the end of A. We'd clearly see that we'd be redrawing A on the end of B. And we would clearly see that the resultant would be from the start all the way to the end like that. That would be C. So it's in a very different direction to the one that we originally had said. The students that do a line which goes from here to here are just writing complete nonsense. The direction will be wrong. Now, for a right-angled triangle, they'll get lucky. For a situation where the components A and B are perpendicular, they'll get lucky, and the resultant will actually be the right value, but the direction will be wrong, and directions are an important part. But clearly this is a right-angled triangle, so let's just get a black pen out, and let's say that B, which is equal to 4 units, and A, which is equal to 3 units, would make C, and you wouldn't need to use a calculator to know that this is a 3, 4, 5 triangle, is 5 units, because that's a right-angled triangle. So we would know the resultant by using Pythagorean theorem, which is that C is going to equal the square root of the sum of the squares of the other two sides. And I'm just going to stick with my nice color code because I've started now and it looks pretty, so why don't I finish? A squared and B squared. Or we could say that C squared is equal to A squared plus B squared. Pythagorean theorem. Let's just make a little note of that. Probably a capital P. Pythagorean. But what about the direction of C? Well, are we going to express the direction of C relative to A or relative to B? And the answer is it doesn't matter as long as we are clear which it is. So let's determine the direction of C relative to B. So what we're saying is how many degrees anti-clockwise from B is C. That's what we're showing here. B is pointing directly to the right. C is rotated so that it is anti-clockwise by some angle. And so to determine that angle, theta, we're going to use arctan. which is the inverse function of tan. On many a calculator, it'll be written as tan to the -1, but in a previous video lesson, I explained why I disliked that notation, because it's rubbish. And so the angle is going to be the arctan of the opposite over the adjacent. So that's going to be the opposite is, in this case, A, and I can wait for my pen to start working, A, and the adjacent is going to be, in this case, B, and then we have our nice expression here. And if I plug in the numbers into my calculator, so this would be 3/4 in this particular case. Just lift out my calculator and do a bit of tapping. My calculator of choice lists it as a tan rather than as tan to the -1 because it's better. You get 36.9 degrees thereabouts. 36.9 degrees. The calculator says 36.869897645. The first 4 digits are 36.86, but obviously if we're going to round this to 3 significant figures, that third digit, the 8, will round up to a 9. Be careful with rounding. So we've now expressed our vector A plus B. We could say that A plus B, and make sure it's clear it's a vector sum, is not going to be 7. 3 plus 4 is 7, but these are vectors. So this is going to be equal to 5 at an angle of 36.9, well, maybe I should put the unit in there as well because it's meters. 5 meters at an angle of 36.9 degrees from, this would be anti-clockwise from, so I might as well write it in code, ACW, anti-clockwise from B. Now, I didn't have to use a scale diagram for that. I did a quick sketch of the diagram so that I could visualize what the resultant was. But what I didn't do is, and it's a vector, so I'll put an arrow over the top. What I didn't do is draw a scale diagram, figure out what the scale is, measure it to scale, and so on and so on and so on. I just used Pythagorean theorem to add these two vectors together. And that's very, very useful. Now, what if the vectors are not at right angles? Well, in that case, what we have to do is figure out a bunch of vectors that are right angled to each other so we can add them together. And to do that, we have to understand how to resolve vectors into perpendicular components. Resolving vectors means figuring out the components. Vectors into perpendicular components. You could do this graphically, of course. We're not going to, because this is A level. What we're going to do is to work algebraically. So let us suppose we have some vector. I'm going to use purple for this. We have some vector, let's just call it C, because I've made all my purple vectors C so far. Then there are different components that we could choose. As long as the components are perpendicular, it counts. So we could have a component like this and a component like that as long as they are perpendicular. They would be components of vector C. Or we could have a component here and a component here. As long as they are perpendicular, they are perpendicular components of C. Now, we don't have to have perpendicular components. We could have C being expressed as this vector plus this vector plus this vector plus this vector. It would be dopey. We'd never do it, but it would still be valid. So sometimes, and you'll get this later on in the course, we're going to be resolving into perpendicular components that aren't vertical and horizontal because we're interested in things like inclines, inclined ramps, or inclined planes. At the moment, we're going to stick with just resolving into components that are horizontal and vertical. So we've got a component that is horizontal, which is definitely perpendicular to a component that is vertical. So we're going to keep it nice and simple like that. We have our two vectors. Let's go ahead and call this one here A, because that's what I've been doing, and calling this one here B, because that's what I've been doing. And as long as this is 90 degrees, they are perpendicular components, then we can use very straightforward trigonometry. But we do need to know an angle. Now let's suppose that it's this angle we know. If it's the angle to the vertical, we just draw the triangle in a different way. But we've got the angle to the horizontal. Let's label it theta. So what is A equal to? The component A is equal to C multiplied by the, in fact, I don't need that. Let's just put C multiplied by the sine theta. And what would B be equal to? B would be equal to C multiplied by the cosine of theta. So we've got a direction in there because what we're measuring theta relative to. And if we wanted to, we could chuck some unit vectors in there as well. Usually the horizontal unit vector is written as I, and it just means that we're looking horizontally, and J, which means we're looking vertically. I and J are unit vectors. That's what we would say there. So we could say that C is equal to the magnitude of A plus J, told times J. So A times J, that's the Y component, plus B times I, that's the X component. Using the notation here, why I chose to make A the Y component and B the X component, I will never know, because we usually do that the other way around in mathematics, but it's okay, it's showing what I need to show, so I don't care. So I and J, with those little circumflexes, those little hats on them, those little triangular bits at the top of them, indicate that they are unit vectors, and unit vectors have a dimension of nothing. They've got no dimension, they're dimensionless. Let's just make a little note of this. Unit vectors, so they have direction, yep, but they don't have any dimension. They're not lengths, they're not times, or anything like that. They don't have any units like that, and they have a magnitude equal to 1, but with no dimension, no units, and just the direction. And by convention, I is the horizontal direction, J is the vertical direction, and K is the direction coming out of the plane. So we could represent our vector like that. Okay, so this is how we resolve our vectors into perpendicular components. Why should we do that at all? Well, let's suppose I'm now going to algebraically add, and I think this is going to be the last part of this lesson. I'm going to algebraically add two vectors together, but they're not perpendicular. So let's just make a note of algebraic addition of non-perpendicular vectors. Algebraic addition of two non-perpendicular vectors. Quite a mouthful, but that's what we're now going to look at. So what we're going to do is we are going to calculate the components, add the components together, and then use Pythagoras on the perpendicular components. So let's suppose I've got vector A doing something like this, and vector B doing something like this, and they are clearly not perpendicular. Okay, absolutely clearly not perpendicular. We've got A doing that, and we've got B doing that. Now we could graphically add these together. Of course we could, to get this vector here. A plus B is C, and I'll just label that as C, just so that we've got it on here. And I can make a little note, I'm just going to use black for this, and say that the vector A it's a vector addition, so we need to make sure we've got an arrow over the top, plus the vector B is equal to vector C. It's a vector addition. We could do that, but look, the vectors are not perpendicular. So what are we going to do? Well, what we're going to do is we're going to take each of these vectors, excuse me, sorry, a little bit of a cough. We're going to take each of these vectors and we're going to break it into two components. Now, you don't have to actually do it with both of these. I'm going to, but what you can do is you can choose to resolve them to be parallel and perpendicular to the other vector. So I could, let's just delete that, I could find the component of A that's parallel to B and the component of A that's perpendicular to B. But to actually show how to do this, it can be slightly easier to just work out horizontal and vertical components. So let's do that. So there's my horizontal and vertical component of B, and these are definitely right angles to each other. And let's do the same thing for A. I've got my horizontal, well, let's do the vertical one first. Vertical and horizontal, it doesn't quite go far enough. One more time. Vertical, there, and horizontal component of A, and they would be in these directions, here and here. You see why sometimes I'd like to draw the arrowhead part way along instead. So you can see what we're doing there. We've actually now got 4 components, and I can label them. I'm just going to use orange to label those components of B. I'm going to call this one, I don't know, B. Let's choose my pen tool. Let's call this one B horizontal, so we could call that BX. And let's call this one B vertical, so we could call it BY. And we can do the same thing over here. This is AY, and this is AX. So we've got those two components of A and those two components of B, and we're going to add them together. So how do we do that? Well, let's do it graphically first, so you can see how this is going to work. I'm just going to move this over a bit, give myself a bit more room. I'm going to duplicate, in fact, let's duplicate all of that, and then we can delete the bits we don't want. If you're playing along at home and drawing these notes, you're going to have to redraw all this nonsense. Let's just get rid of them. So there are the components. Let's do some moving around. We can move the X component of A onto the end of B. We can move, we can move the Y component of B, changed its shape. Oh, let's get rid of the perpendicular sign because it's clearly perpendicular, we know that. So let's move B onto the end of there, and then we can move this onto the end. Now notice that the AY is the opposite direction to the BY. So I'm going to pop it like that. It should be vertically. You can see my diagram's not perfect, but actually that works out quite well because it means that we've got more chance of being able to see what the hell is going on. There we go. So I've done BX, add AX, they're both parallel. BY and AY are parallel, but they're in opposite directions. So I'm starting to calculate my resultant vector. I'm starting over here. I am going to go BX, AX, BY, and then down to AY. Just like that. So what's my resultant going to be? My resultant is going to be, starting here, ending here. So my resultant is going to be this small triangle down here, and I can clearly see that. Let's just move the BX label so that it's not getting lost in amongst the purple one. Let's change its shape again. Let's just put it up there. So that's going to be my vector there. So all I need to do is work out what the components, the perpendicular components of that C are. Well, the horizontal component is easy. C in the X direction is just going to be, let's just make it black, is just going to be B in the X direction plus A in the X direction. You can see that. Look at the triangle. What about the Y direction? Well, slightly different now. C in the Y direction, the Y component of C, is going to be AY minus BY in magnitude. AY minus BY. They're in opposite directions. Now, I could do BY minus AY and get a negative number because it's going down if I choose up to be representing vectors that are positive and down to be representing vectors that are negative. But I really don't need to do that. I could just label it like that. Let's just put this over here so that it's out the way. So we've got step one, a quick sketch. Let's label some of these. We had step one, a quick sketch on what the hell's going on. Then step two, which was the components of the B and A. Then step three was adding all those components together to make a right-angled triangle. And then lastly, it's much more straightforward what to do. So if you know the direction of B, you can calculate BY and BX. If you know the direction of A, you can calculate AX and AY as well. Okay, this is a right-angled triangle here. This is a right-angled triangle there. You can calculate. Once you've got the calculation of the values of AX, AY, BX, and BY, you're just adding those components. So what we're actually saying here is that C is equal to AX in the I direction plus BX in the I direction plus AY in the J direction. For some reason I'm defining down as positive, minus BY in the J direction. And obviously we can factor out the I, factor out the J, and we end up with AX plus BX in the I direction and AY minus BY, because of how I defined my vector directions, in the J direction. And then we do Pythagoras on the I component, on the X component and the Y component of C, because that's exactly what we did before. Once we had perpendicular components to calculate the resultant, it's no different here. I'll stop there. That's a good introduction to vectors, and it takes it from GCSE to A-level. I would say I tend to think that addition of vectors and components of vectors is something that A-level students ought to know before they start A-level. That's why I include it in my transition work. That if you didn't understand it before, hopefully you've got more of an understanding of it now, and do lots of practice questions so that you can become really comfortable and fluent with using vectors. Because you're going to need to for your A-level physics. They're not a bolt-on extra anymore. They're really, really important. Right. I hope that was useful, and I hope I see you next time. Bye-bye.